Hello students, and welcome to the Unit 5 review for your Algebra 1A course. In this unit we studied linear systems. Now all that is having more than one equation or more than one line on a graph, but these are some of the most practical tools that you need for working in algebra because many situations require you to represent two different sets of data and to find out when they coincide. In this unit, we talked a little bit about compound sentences that use the word and that might sound like English, but that's where we get into systems of equations and inequalities. These are found by finding either the intersection of individual solution sets or finding out if there aren't any. So we'll review these concepts. You had quite a bit of vocabulary in this unit. On your unit test, you are going to need these, so if you haven't downloaded the glossary that comes at the end of the unit, make sure that you have at least these words in your notes so that you understand what your questions are asking. I'll go over them a little bit as we go through the review, but if you need to stop the video, stop it now and write these definitions. Now, a system, as I said, is more than one equation or more than one set of solutions. And if you are looking at a system of two linear equations, it's classified by the number of ordered pairs that satisfy both of those equations. Since the graph of each linear equation is a line, three possible situations occur. So here you can see that we might have an inconsistent setup. I've got two lines graphed on the same graph, and you can see because the lines are parallel, there is going to be no solution. This is referred to as an inconsistent system of equations. They never coincide, so they're inconsistent. Most equations systems that you'll get are consistent. Either they intersect at one point where they're considered independent and have one solution, or they are the exact same line. That means they have infinite solutions, because if you're looking for how many solutions there are that fulfill both and they're both the same line or the same equation, they are consistent, but this is called a dependent system of equations. Here are some examples. Inconsistent systems are always parallel lines. So if you're looking at the graph, easy peasy. But you might not be looking at the graph. You might be looking at the equations. What do you know about parallel lines? Well, if you can determine the slope of each equation, if they match, you know that those two lines are parallel and they will be an inconsistent system of equations and will never intersect. Consistent independent systems are intersecting lines. The lines have to have different slopes. If they do have different slopes, they will always intersect at some point. So again, determine the slope of each equation. If they don't match, the system is consistent and has one solution. Consistent dependent systems are the same line. Now these are going to have the same slope, obviously, but they will also have identical y-intercepts. So unlike the inconsistent systems that are parallel lines that have different y-intercepts, these will have the identical y-intercepts. So first step, determine the slope of each equation. If they match, determine the y-intercepts. If they match, the lines are the same and there are an infinite number of solutions. Take a look at these two equations. I've got y equals 1/2 x plus 1 and 2y minus x equals 2. They certainly don't look like the same equation. In this first one, because it's written in slope-intercept form, I can easily tell that the slope is 1/2 and the y-intercept is 1 just from looking at the equation. However, this other one needs to be solved for y for me to determine if the slopes are the same and if the y-intercepts are the same. By adding x to both sides, I get 2y equals x plus 2, and by dividing everything by 2, I get y equals 1/2 x plus 1, the exact same solution. The slope is 1/2, just like the other one, and the y-intercept is 1, just like the other one. So these would be considered consistent dependent systems. Now, solving systems by graphing is actually one of the easiest ways. And if you haven't gotten used to using Desmos.com, it's going to be your friend in this unit and especially on this test. So make sure you have that open in another tab. By graphing the linear equations together on the plane, you can find the points that they have in common. Either they'll be parallel, they'll be the same line, or they will intersect. So for instance, if I had the equation x minus 2y equals 3, I would change this up a little bit to make sure that I've got it in slope-intercept form because that's the easiest form to graph. By subtracting x from both sides, I can get negative 2y equals negative x plus 3. By dividing everything by negative 2, I get y equals 1/2 x minus 3/2. So I know that the slope will be 1/2 and that the line will pass through the y-intercept at negative 3/2. So I put my negative 3/2 down on the graph and I go up 1 and over 2 and put another point on the graph, draw the line in between, and that would be this red line. If I had this other equation to determine if it was the what the solution was or what the intersection was, I would subtract 5x from both sides, giving me 3y equals negative 5x plus 2. Then I would divide everything by 3 to get y equals negative 5/3 x plus 2/3. And I know that this line will go through at positive 2/3, which is up here. Then I'm going to use the slope, which is negative 5/3. So I'm going to come down negative 5 and over 3, which would actually be off of this graph, but it would be down here. And then I would draw this blue line. And you can see that the lines clearly intersect. Now, we don't need to know just if they intersect. We want to know exactly where they intersect. And I can tell from the graph that they intersect right at the point 1, negative 1. So I know that this point is the solution to the system because it satisfies both equations and it is the one and only point or set of coordinates that satisfies both equations. The substitution method is one of the most common methods that you'll use for systems. Graphing can be a little bit tedious, and sometimes it's easy to substitute, sometimes it's a little bit complicated, but using your algebra skills that you've already learned, it shouldn't be too hard. So, one of the things that's important is to look at the equations that you're given when you're looking to find the system, and using substitution, you're really looking for one easy way to get one of the variables by itself. It doesn't matter which one. So looking at this system, I'm looking at the top equation. It has an x that has nothing being multiplied by it. I know that I can isolate it by doing one step, and that's just adding 2y to both sides. So once I do that, I get x equals 2y plus 3. Now why do I want to do that? Because once x is isolated, I can use whatever it is equal to, 2y plus 3 in this case, instead of x in the other equation. So here the other equation was 5x plus 3y equals 2. Instead of 5x, I'm going to substitute 2y plus 3 instead of x. That way I only have one variable in my equation and I can easily solve it. Using the distributive property, 5 times 2y is 10y, 5 times 3 is 15, plus the 3y that was already there equals 2. Combining like terms, I get 13y. Subtracting 15 gives me negative 13. Finally, dividing both sides by 13 gives me y equals negative 1. Now, I'm not there yet. I've got the value for negative 1 that's going to work for both of these equations, but I have to go back and take another step and use it instead of y in one of the original equations. It doesn't matter which equation you use because the whole idea is we're finding a solution that will work in both. So find the one that's easiest. I chose 5x plus 3 times negative 1 equals 2. 5x minus 3 equals 2. Adding 3 to both sides, I get 5x equals 5. Dividing both sides by 5, I get x equals 1. I'm just going to check this out to make sure that negative 1 is the solution. in the first equation, 1 minus 2 times negative 1 should equal 3. Well, negative 2 times negative 1 is plus 2, so that's 1 plus 2, and sure enough, it does equal 3. So the solution is 1 comma negative 1, and that will work for both equations. There's another method you learn called the elimination method. When you do this, you set up your two equations kind of like a big subtraction or addition problem, and you line up the x terms in one column, the y terms in another column, and the constants in a third column. What you're looking for is two of these sets to be sort of matching. If they have negative signs, that's even better. What we're trying to do is eliminate one variable from this set so that we can solve for one remaining variable. This particular set doesn't line up perfectly well, but I see that the y term, the y term in the second one is negative, the y term is positive in the first one. If I multiply everything in the top equation by 2, I'll get 2y instead of just y, and that will be the opposite of negative 2y. So I know that when I add these two equations together, the y term will basically disappear or cancel out. So 2 times 2x plus y equals 3 equals 4x plus 2y equals 6. Now I'm going to set it up again, and you can see how nicely these two terms line up. And when I add these two equations, I just do it as if each one were a unit column. 4x plus x is 5x, 2y minus 2y is 0, and 6 minus 1 is 5. So 5x equals 5, dividing both sides by 5, I get x equals 1. Now I can go back just like I did in the substitution method and use my value of 1 instead of y in either of the equations. Instead of x, and put in 1 minus 2y equals negative 1, and add or subtract 1 from both sides to get negative 2y equals negative 2. Divide both sides by negative 2 to get y equals 1. Check it out. If both values are 1, then both of these equations should work. 2 times 1 plus 1 is 2 plus 1, and it really does equal 3. So the solution is 1 comma 1. And if I were to graph these two equations as lines, they would intersect at the point 1 comma 1. What about if we have inequalities like we talked about in the last unit? Well, we talked about how you draw the line first. It can be dotted or it can be solid, and then you shade either above or below the line. So how would you tell where the two solutions intersect? Well, when you shade one of them and then go back and shade the other one, there should be an area where they overlap. That area where they overlap is the solution set of the system of inequalities. So here I've got an example, y is less than negative x. I graphed, remember the technique, I graphed y equals x. I made it a dotted line because it's not actually equal. Those solutions on that line are not part of the solution set, but it is the boundary between the solutions and the non-solutions. Then I graphed the equation y equals x minus 2, that's the blue line, and because it has the equal portion in the inequality sign, I used a solid line, and I shaded below the line because y is less than. So I've done one in blue and one in red, so the overlapping area is easy to see. It's this purple section right down here. And if I checked any particular point, such as 0, negative 4, it should work for both of these equations. Is negative 4 less than negative 0? Yes. Is negative 4 less than or equal to 0 minus 2? That's negative 2. Yes. So as long as my solution is always in this overlapping area, then I know that I have shaded it correctly to show the solution set. There is one other way that you can find the solution of a system of equations, and that's by using determinants. When you do this, you create a matrix And this matrix is a special number that can be calculated by creating these squares. So it's just an array of numbers. So for instance, if you had these equations 2x minus y equals 5 and x plus 3y equals 7, you will take the coefficients of the terms to form the matrix. I took the 2 from the x, the -1 from the y, the 1 from the x, and the 3 from the y, and I put them in a little array. And to calculate the determinant of this, I'm just going to do diagonal products. 2 times 3 minus 1 times -1, and then I calculate it. So 2 times 3 is 6, minus 1 times -1, which would be minus -1, would be plus 1, and so 6 plus 1 equals 7. So 7 is the determinant of this set of equations. Find the determinant. In this case, if you are already given the matrix 5, 4, 8, and -2, remember, just do diagonal products, 5 times -2, and subtract the product of the other one, 8 times 4. Now it is important that you do these in the right order because we're talking about subtraction here. So always start from the top left and multiply by its diagonal, and then go to the bottom left and multiply by its diagonal. In this case, I've got -10 minus 32 would be a total of -42 for the determinant of these equations. Now, I've got here the determinant is calculated by AD times minus BC. You might want to copy this into your notes because this is not something that we use very often, but it is an option, and there are some calculators that give you the option of using a matrix, and if you have those, they're very often used in calculus. There are also a couple of other determinants that you might be asked to calculate. Instead of using the coefficients of the x and y terms only like we did in the previous slide, you will not use the coefficient of y. Instead, you substitute the constants in the equation for the y coefficients. So here's our equations. We're going to use the coefficients of the terms to form a matrix. So our matrix now is 2, 5, 1, 7. I'm still using the coefficients of the x terms, 2 and 1, but now I'm switching over to the 5 and the 7 because I was asked to find the y determinant. That means I'm not going to be using y. It's a little counterintuitive. They're asking you for y, and so the y is the one you're not going to use. You'll solve these in the same way though. Diagonally from top left, 2 times 7 minus 1 times 5, and in this case it would be 14 minus 5, or 9. So 9 is the y determinant of this system of equations. Now, there are a lot of practical ways that you can use systems of equations. Here are some examples. One number is 7 more than twice another. If their difference is 22, what is the larger number? We've been able to solve these previously by doing a little bit of guess and check perhaps, or writing an equation where we find the first number and then go back and find the second. But here we can do it with two variables and find them both at the same time. I'm going to translate directly. One number, that's x, is, whenever there's a verb, that's where your equal sign goes. 7 more than will be 7 plus, twice another. When it says another, you cannot use the same variable. It's 2 times a different variable. In this case, I've chosen y. If their difference is 22, so I'm showing the difference, x minus y, is my equal sign, 22 is the constant. What is the larger number? All right, let's solve this. Write the equation in standard form so that they line up correctly. So that means I'm going to have to subtract 2y from both sides of this first equation to get my columns lined up. At this point, I'm going to look for a way that I can eliminate one of these. And before I showed you addition of two equations, this time I'm going to use subtraction, and both are available to use. I just have to remember in the subtraction I'm subtracting each column. X minus x is 0. Negative 2y minus negative 2y would be plus y. So negative 2y plus y leaves me with just minus 1y. And 7 minus 22 is negative 15. That means that negative y equals negative 15, and if I multiply both sides by negative 1, I get y equals positive 15. Now I'll go back in, substitute 15 for the y in either of the equations, and solve for x. This tape I did the top one because it seemed a little easier. X equals 7 plus 2 times 15. 2 times 15 is 30, plus 7 is 37. This is the larger number. And I know it's a larger number because the sentence said one number is 7 more than twice another. Now, some equations are very complex. These involve some fractions perhaps, and maybe there is no obvious way that you can solve the system. So let's look at some of these. The numerator and denominator of a fraction are in the ratio of 3 to 5. So I've written this out as n over d, numerator over denominator equals 3 over 5. If the numerator and denominator are both increased by 2, that's where I used my n plus 2 and my d plus 2, the fraction is now equal to 2/3. If n is the numerator and d is the denominator, find the fraction. Okay, so I've got a setup in the left and a setup on the right for two different situations using the same numbers. That means I've got a system of equations that I need to solve, but they're not really in equation form. So remember, if I have two fractions or ratios equal to each other, that's called a proportion, and I can cross multiply to make that an equation. Starting from the top left, n times 5 is 5n, and d times 3 is 3d. I know those two quantities are equal. I can do the same thing with this more complex one. N plus 2 times 3 is written in parentheses. D plus 2 times 2 is written in parentheses, and I have to take an extra step here and use the distributive property. 3 times n is 3n, 3 times 2 is 6, 2 times d is 2d, and 2 times 2 is 4. Now I've got two equations with the same variables. I'm going to write them both in standard form so that I can line them up. Here I'm just subtracting 3d from both sides to make 5n minus 3d equals 0. And here I have to do some combining of the constants. I'm going to subtract 6 from both sides to get negative 2, and subtract 2d from both sides. So now I've got 3n minus 2d equals negative 2. Now that they're nicely in the same form, I can line them up. And in this situation, they didn't line up exactly because I had a 3d and a 2d. But that's okay because I can multiply any equation by any number as long as I multiply every single term by that number. So I'm multiplying the first one, the 5n minus 3d, by 2. That gives me 10n minus 6d equals 0. And I'm multiplying the second one by 3. That gives me 9n minus 6d equals negative 2. Why did I choose these numbers? Well, I wanted one set of these numbers to match up and have the same coefficient. There wasn't any way I could just multiply one of them and have them match up. So I could have either chosen to multiply this by 3 and this by 5 to get 15s, but I thought it'd be a little easier to multiply this by 2 and this by 3 to get 6s. It's kind of like finding the common denominator of fractions. I'm looking for a number that's a multiple of the two simplest numbers. Now that I've got them lined up and my 6d's match up nicely, they have the same sign, so again I'm going to be subtracting these. 10n minus 9n is n, negative 6d minus negative 6d would be plus 6d, and that cancels to 0, and 0 minus negative 2 is 0 plus 2, or n equals 2. Now I can use that 2 for n in either of the equations. 5 times 2 is 10. 10 equals 3d. Dividing by 3 gives me 10/3 for d. So the solution is 2 and 10/3. There are a couple of essay questions in your test that I wanted to alert you to because they are fairly complex and they're going to use everything that you learned in the unit in order to complete them. Jean babysits for $7 per hour. She also works as a tutor for $9 an hour. She's only allowed to work 18 hours per week. She wants to make at least $65. So if X is the hours that she works babysitting and Y is the hours that she works tutoring, model the scenario with a system of inequalities. Okay, you can see this is fairly complex, but we're going to use the keywords to write the two inequalities. First, we know she babysits for $7 an hour. This is a rate. I know that this is going to be multiplied by X because it says per hour, and I'm using X to represent the hours. Babysitting. So 7X is how much she earns babysitting. 9Y is how much she is earning while she tutors. Together, that amount of money has to be at least $65 because that's how much she wants to earn. Also, she has another restriction. The total number of hours, X plus Y, has to be less than or equal to 18 because that's the maximum she's allowed to work. After all, she's a student. Now, let's solve as equations. I just substituted an equal sign for these inequality signs and use the same techniques. If I solve this one, I would subtract 9Y from both sides. Let's see, it's easier to solve this one. So subtracting Y from both sides, I get X equals 18 minus Y. Then I can use 18 minus Y for X in the next equation. So 7, instead of 7 times X, I'm using 7 times 18 minus Y because it equals X, plus 9Y equals 65. Using the distributive property, 7 times 18 is 126. 7 times negative Y is negative 7Y, plus the 9Y that was already there equals 65. Adding 9Y minus 7Y gives me 2Y, and subtracting 126 from both sides gives me negative 61 on the right. Dividing both sides by 2, I get Y equals negative 30.5. Substituting negative 30.5 for Y in either of these inequalities, X minus 30.5 is less than or equal to 18. If I add 30.5 to 18, I get X is less than or equal to 48.5. Now, what's the problem with this? It checks out mathematically. I can see that I have graphed it on my graph, and I've got some overlapping space of the hours that she possibly could work both of these jobs and hit both of these restrictions. However, this can't be possible because if she works 48.5 hours babysitting, number one, that's more than 18 hours all by itself. And she can't possibly work negative 30 hours at her tutoring job. Neither of these numbers can be hours that she works. However, the graph of this system of inequalities does show an overlapping shaded section that is the solution. So if this were some other type of situation with these same equations, it would have a solution, but it certainly doesn't make sense in this situation. Here's another one. A taxi cab charges 45 cents per hour in addition to a $2.75 flat rate fee. Susie has $15 to spend on a taxi cab ride. The taxi driver will not give anyone a ride unless they're going somewhere that is more than 1 mile away. Model the scenario with a system of inequalities. Okay, so let's look again at these keywords in the problem to write these. I know that 45 cents is a rate, and it says per mile, so it's definitely going to be multiplied by the number of miles that she drives. Let's call that M for miles. So here's my 0.45 M, but in addition to that amount of money, she has to spend $2.75 on the ride. She only has $15, so whatever the total is has to be less than or equal to 15. Also, she has to go more than 1 mile, so M is greater than 1. These are our two inequalities. To solve them, we've already got M pretty much isolated. So I could substitute 1 in, or let's see. That one's already solved, and this one could be easily solved by dividing both sides by 0.45. Then I would get M is less than or equal to 27.2 repeating. Now I've got two situations that both have to be true, so I've got the word and in between them. That means I'm looking for the area where they overlap. The reason why I'm not graphing this on the coordinate plane is because I've only got one variable, and that's the number of miles. So the solution is 1 is less than the miles is less than or equal to 27.2 repeating. And then I'm going to graph it by putting an open dot on 1 because there's no equal portion to the inequality sign, a solid dot on 27.2, and then I'm going to graph the area in between. She can take the taxi any number of miles in between 1 and 27, and she would be able to spend less than $15, and it would be more than 1 mile. Sometimes you do have inequalities with 2 variables, and that's okay, like the one that we showed before. That just means that you're going to have a shaded area that overlaps. This is a question from your test. It says, write an inequality that represents the following scenario. Peter's at a local pizza shop. He wants to purchase pizza, pies, and breadsticks for a party. The cashier tells him that pizza pies are $10 each, breadsticks are $3 each. Peter can't spend more than $100. Let y represent the number of pizza pies purchased, and let x represent the number of breadsticks purchased. Okay, so we're going to use these keywords. We know that it's $10 for each pizza, and y is the number of pizzas. It's $3 for each breadstick. I hope it's not each breadstick, maybe each set. And that's going to be multiplied by the number of breadsticks. Together, they cannot equal more than $100. They could equal 100, but otherwise they have to be less. So to graph this, I'm going to put it into slope-intercept form by getting y by itself. Subtracting 3x from both sides, I get 10y is less than or equal to negative 3x plus 100, and dividing everything by 10 gives me y is less than or equal to negative 3/10 x plus 10. To graph this, I'm first going to choose 10 as my y-intercept, and then I'm going to go down 3 and over 10 to get to my next point. And because y is less than this value, I'm going to shade underneath it. Anything in this shaded area is going to be okay for him to buy as far as the number of pizzas. Now you notice a lot of this is in the negative category. Well, he's not going to buy a negative number of pizzas and a negative number of breadsticks, so all of this area is not going to work. But anything in this little triangle in the positive area, such as maybe 2, 1 or something like that, he could buy 2 pizzas and 1 set of breadsticks and still be under $100. Here's another question from your test. Katie's buying souvenir gifts for her big family back home. She wants to buy everyone either a keychain or a magnet. The magnets are on sale for 60 cents each, and the keychains cost $2 each. She has to purchase at least 36 gifts, but she has to spend less than $40. Let x represent the number of keychains and y represent the number of magnets. Model a scenario with a system of inequalities. All right, well, we know that 60 cents has to be multiplied by the number of magnets, which we are using x. The magnets are on sale for 60 cents each. The key rings are 2 cents each. So let's change this up and use y to represent the keychains, and x the number of magnets, because it looks like I put my 0.6 next to the number of keychains instead. Okay, so let's say that she's buying these magnets. That's going to be represented by x. $2 for each keychain. Together, they have to add up to something less than $40. It doesn't say she has $40. It just says it has to be less than, so we're going to use the plain less than sign. And together, they have to be at least 36, so greater than or equal to 36. I can solve this one easily for x by subtracting y from both sides, and that's great because then I can substitute 36 minus y for the x in this other equation and solve. Negative 0.6 times 36 is 19.2, minus 0.6 times y is 0.6y, plus 2y equals 40. Then simplifying by combining the y terms, I get 19.2 plus 1.4y. equals 40. Subtracting 19.2 from each side, I get 1.4y equals 20.8. So dividing this, I'm not going to get an exact number, but that's okay because she can't buy a piece of a keychain or a piece of a magnet. So I end up with y is approximately equal to 15. If she did buy 15, and we're using y for the magnet, no, we're using them for the keychains. If she did, then x plus 15 is 36, so she would buy 18 of the other. So here is one possibility for what she can buy. The solution 1518 is definitely in the shaded area here. Now, if we wanted to solve this by graphing, we would have put our 0.6x plus 2y is less than 40 in as one of these lines. The blue area would be shaded below, and the other one would be shaded above where y equals 36, or x plus y equals 36. So the solution 1518 does make sense because it says that she can buy 18 keychains and 15 magnets. However, there is a range of gifts that she can buy represented by the overlapping section of the graphs. The domain and range are both greater than or equal to 0. So this brings us to the end of our review. I hope that you got something out of it. If you took good notes on those essay questions, those should go a little bit more smoothly for you. If you have any remaining questions, make sure to write those down, and when you call me, we can discuss those. If you have any concerns about whether you're ready for the test or not, make sure to go back and look at your unit quizzes. They have very similar questions to those that you'll see on the unit test. Otherwise, good luck on the test, and I'm looking forward to your phone call.